Welcome to part 5. In the previous part, I showed you how to identify labels that were automatically generated because of code that was actually no code, but data that was interpreted as code by default. And in that part, we found that the data area from 4000 to 7FFF should actually be free of labels because it's dynamically addressed as extended memory. Therefore, every label pointing there is some kind of false positive, and we set the code to the code that generated these labels to be data. In this part, I will show you what we can learn from the sections where we identified strings now, because behind every string we had seen some kind of data, garbage, crap. We don't know yet what it is. And there are other nice examples how to identify where so-called jump tables are. And this is the topic for today. Before I start, I would like to show you one setting that I had done previously. I have reduced the number of words per line and bytes per line and characters per string to the given values that you see here. This makes it easier in this small display to actually get and see what's going on there. Okay, so let's have a look at the labels as usual. So we have here the automatically generated labels. We see there are no labels anymore in the area of 4000. We see there are some labels in the upper area before the ROM starts, so up to BFFF. Maybe we look at them first to see if we can learn. So here is a jump subroutine to BD5C, and this has multiple occurrences. So let's see what's there at BD5C. And here again at BD5C we see there is no label, and we see right in the middle of a code there is some strange things again, a byte statement, so no valid app code. So this is an indicator that maybe here there is again data interpreted as code where it shouldn't be. So we know that if there is a jump subroutine at BD5C, then there must be a routine starting at BD5C. So let's look what's there. 5.8, 5C, oh no, that's PC, BD, 5C. And here we see some 30, 38, 28, and here actually code starts. Yeah, so this is an LDX or LDY, so we know this is code. So we change this explicitly to be code. Still, it doesn't show it like this. Why? Because it assumes the previous sections are also code, and the last opcode it finds is a 3-byte opcode, so it simply doesn't match the starting point of the code. That means we have to turn all the rest here, where we are fairly sure that it's no code, into data. And we see there are labels, so maybe we can use them as an indicator. So this label here is the target of a branch equal. So this is most likely code. Again, this label is only used in one location, and it's used as with a load via index with the X register. So at least we know the first byte probably is data, but which byte really is data depends on the values that X takes. So let's look at the code location where this X is initialized, and we see there is a loop that copies starting with X equals 4, decrement branch as long as it's positive, branch plus. That means from 4 to including 0 bytes are copied from that location, and that means we have here 5 bytes, 1, 2, 3, 4, 5 bytes of actual data. That is no code. And if we now set this here to explicitly to be data, automatically this label here is generated. The jump target is generated, it finds a real label here, and this undefined or unknown label is now removed from this list. So we have one more. So we have something here, and there's a branch, and that is now a nice example of what I wanted to show. This is a branch into nowhere. Yeah, so we have here some data and then something that we have not explicitly identified as data, and therefore it interprets it as code by default. But when we look at this, we see that actually all these patterns are something that's like ASCII, and they are terminated with 9b. 9b is the end of line character. So obviously this, even though it didn't look like a string, it is actually the string 0, 0. So we turn this into a string. And again here we have minus 0, 0, so this must also be a string. I'm actually not sure about this 0 here, so it might not be part of a string, but we leave it like that. And again here we also have that. This is 0, something. Let's turn it into a string. Whether it's a string or data, it doesn't hurt. It just determines how this is visualized. And also here there's a branch which is not actually a branch, but it is 0 followed by the end of line. So this is also a string. Then this continues up to here, and we see there are even more things, and they all end with 9b. So now I'm a bit brave and set all of this to just be text. And we have eliminated a number. Oh, we forgot something. Also here, we eliminated now a number of false positive code locations, and the corresponding labels and branch target, they are now also gone. So scroll up to the label definitions. And now we see that in the complete area of the main code, there are no pseudo labels anymore. We see some strange things here. So CA would be in the operating system area. There is no use subtracting anything from the operating system. So this is also a hint that that's something that shouldn't be code. And we end up again in one of these sections where we have always mixed text, code that probably isn't code, text again. So we set this explicitly to be bytes. And we do the same thing here. Thereby eliminating labels that are generated by false positive code. And also we see again here some patterns. So this is 5, 6, B6, 5B, B6, B6. So we will be there in a minute, and I will show you why this makes me curious. So we set it to bytes first. Still there is quite some crap that we have seen, but let's go do it step by step. Again, here there's a comparison with something in the operating system that's for sure not intentional. And the last thing here. Yeah, that's now actually interesting. In the area of D800 to DFFF, there's the so-called MathPack. This is part of the operating system that contains floating point routines that can be reused from the operating system and from your own code. For these defined routines in this operating system, part of the operating system, there are also predefined labels that come with DIS6502. So see here the floating point routines, at least the ones that it knows by heart. And probably this is a rather complete list of the official entry points into the floating point pack. But let's see, this is So, but here we again have a call which is in front of some others that are obviously related to the floating point area, but we don't know what it is. I would have to look it up in some kind of operating system listing, but what we can do is we can assign this to MathPack LDE95. So maybe this is something official, maybe not. In case it is official, then everything's fine. We just have to add the label according to the documentation that I will probably find. If it's an illegal entry point, then this might actually be something that causes failures in if alternative OSs like Altera OS are used. So people should avoid also illegal entry points to the OS wherever possible. And now we see everything that's left is in the RAM area. We also see here that there are some code locations that are not used as data but as targets of jump and JSR. Not many, but there are some. And if you remember, I cut off everything that's before this part of the code because I said this is where the bootloader starts, and right before the bootloader there should only be the DOS. Maybe this is DOS, maybe this is not DOS, we don't know, but it's a reasonable low amount of labels, so we can have a look in Altera in a separate part what these routines are about and if they can be extracted or if they're relevant at all. So, and now, as promised, let's search for the jump tables. I said the jump tables, from what I've seen, are often related to these sections. So in these sections we find texts, and every text, every word, is ended with an inverse character, and we see there are multiple of them. And here I have turned part of the non-text data that's following this into bytes. So if I do this here and set it to bytes, then I cannot really see any pattern. Here we have some bytes, and if I look at those, I can actually see a pattern. So this is 96A0, C1A0, ACA1. Yeah, and you can realize this pattern even better if I turn this from bytes into words, because then you see that these are most likely often ascending sequences of addresses. And if you look at the line above, you will be able to match what this is. So we here have a string that is called load safe, and there is an address for it. And we have here something that's called text, and there is an address for it. So this is most likely a jump table for a routine that takes this text here, or finds this text as an index, and then finds the corresponding entry in the jump table. So what can we learn from this? That this is actually not any word, but it is a label. So we go here and we say this is not just a word, this is a label. And if we go here, then we see A1. This has now been defined as a label. I would have expected something else. I would have expected that there is some code starting at A096. So let's look what's there at A096. A09. Where is A096? This is 90. 1, 2, 3, 4, 5, 6. So why is this? Why didn't it put a label here? Well, at A096 there is this, and this is right in the middle of a jump opcode. Yeah. So obviously this is we have some offset problem here. This is actually a location after a jump, but it has no label. So it means by now it is unreachable code. But what you can assume is that actually that label that we were trying to define is here. So which address would that be? That would be 9A097. So going back, what was the label that we had added based on the A097? And this is A096. So what's the reason? The reason is a typical pattern to implement jump tables is not to actually put the address there, but to put there the address -1. And the reason I will show you in a second, because I know there are other locations where we see actually the implementation of the read access to the jump table. But let's just, for the time being, just believe me that this is a label and that this is not this label, but that this is label A097 -1. So let's see what happened. A091. Oh, it didn't do it. So I do this differently. I add a user equit. A091 becomes LA091. So now we have the label here. And we see this, there's a routine starting. And we can give it now even a better name. We can rename this load save. And we also have to adapt this. Yeah, so technically these are handled as two different labels, user labels, but ultimately in the source they will appear as one. And we can now continue. We would turn this actually A1. We would say this is also a label. And AC, AO, everything up to this point here is definitely a label. And these labels have no counterparts yet. I would have to do the same thing that I did for the load save. So actually this label here, which one was it? This label here, I would A0C1. So probably we'll find something at A0C2. Yes, exactly. There is A0C2. And so I define user equit A0C1 is LA0C2 -1. And we see that here it is now defined, and we can rename we could now rename this label to text and continue like this. What you see is from this crap that was previously defined as code, and then we turned it into bytes, and then we realized that these bytes are actually words. Do the same here. These are all words. And they are not just any words, they are actually labels. Yeah, and this is the jump table, and you see that there is a corresponding address -1 for all of this. So let's go here. These words, they are all labels. These two, A3AF, A3FF. You see, this is always ascending addresses. This is also a frequent pattern. Yeah, simply because if you do these things or you have some kind of compiler that optimizes it, it will automatically put the addresses usually in the subsequent things that you implement in subsequent address spaces. So we also see that there is some kind of more data attached behind these jump addresses. So this is probably not a word. But we don't know yet what it is. And here we have even more. So look at those, A3FF, A4, 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 and then there is again data. So these are all labels. And the rest is no code, the rest is data. And again, DB, A3, 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 these are labels. And the rest is data. Yeah, you get the idea. This is how I would go through the complete code now. And for every location where I actually identify things to be labels, I would try to find out if the target is automatically defined as a label, if it is a jump table, or if I have to do this trick with a -1 because it is an RTS table. So let's see, where else do we have maybe some of these text blocks with their addresses attached? I was just scrolling through this. This is the main data part. Text should stick out. Oh, here we have something. Here we have something that's obviously a table that is addressed via index to find something. And there are related tables, but these values don't look like addresses in our address space. That is interesting. Whereas if we look here, we find such sequences again, and again we see a pattern. AC, AB, sometimes the same, sometimes related values, and that indicates that this very likely is again a set of labels. And when we look at one of, let's pick one of the target labels. So this is AC1E. So what's there? And here we see there is something that is not really the start of a code, but we see that the next line would be the start of the code. So again, we have here this off by one issue. And actually it led us to a location where this implementation that I talked about, how to actually jump into a jump table, is implemented. It's exactly this code here. So we have here again label addresses. So BBB from B0 to B2. So we change this to be labels. We don't see any direct usage. Maybe later on it will be generated. So again, these here are obviously jump tables, yeah, to the same code block in the A000 space. Where does it start? Where does it end? All of these are labels. And also here we see, ooh, that's mean. I think I now see what is happening here. So all of this is data. B8. Yeah, but here we can see it. So this is an implementation of a jump table. The routine that starts here loads the accumulator with a value of the index of the routine to be called. It multiplies it by 2 because an address has 2 bytes. It transfers it to the X register, and now it loads the high byte and then the low byte of the target address from the table. So the table starts at ABB7. This means that ABB8 is nothing but ABB7 plus 1 because it's the high byte. And we see it pushes it to the stack, then it pushes the low byte, pushes it to the stack, and performs an RTS. And the RTS simply does nothing else but pull the topmost 2 bytes, interpret as a return address of a JSR, and jump there. So why is somebody doing this? Well, the advantage of doing it like this is you can jump dynamically to a dynamic target without using a vector in the RAM. Yeah, you're implicitly using the top of stack as your vector, but you don't need to reserve something in the 0 page or maybe somewhere else to do an indirect jump. Also, this is often used in the operating system because, again, it doesn't require self-modifying code, which would also be an option, or any special reserved memory location to do this. Well, I think that was it for the time being regarding the jump tables. As you have seen, there is a lot of work for me to do, getting all the jump tables to the right pattern, and if I find something interesting, I will tell about it in the next part. See you, bye.